guys, welcome back to the LearnAPChem series here at LearnAP. In this video we're going to talk about liquids and their properties. So we'll go over surface tension, viscosity, evaporation, vapor pressure, boiling point, and heat of vaporization. If you guys have any questions on this video or anything covered, be sure to leave a comment, or you can also ask in the weekly live streams we do every Sunday from 5 to 6 p.m. Eastern. Other than that, we'll get started. Alright, so let's start by talking about surface tension. Now, surface tension describes the increase in the attractive forces between the molecules at a top of a liquid. Now, so this is sort of confusing to think about, but it makes sense if we draw a picture. So let's say that we have our atoms of a liquid here, and these are being held together by IMFs. This center molecule here is being attracted by sort of four other molecules. But these ones at the top are only being attracted to 3. And so these here are going to be stronger. So that's the concept of surface tension. Now, this means that liquids will try to minimize their surface areas and form spheres. And spheres are simply minimizing surface area. Why that is, you don't really need to worry about. And let's go over some definitions. Now, there's adhesion, which is a liquid's attraction to adhere things. I just find that's sort of a useful mnemonic device so you don't get it confused with cohesion, which is a liquid's attraction to itself. So adhesion, others or adthers, and then cohesion to itself. Now, if a liquid's cohesive forces are stronger than adhesion to sort of a flat surface that this liquid is on, the liquid will bead up. So here our cohesion is stronger than our adhesion. Now, if our adhesion is stronger than the cohesion, our liquid will sort of spread out evenly. So that's just something to sort of know and be familiar with. Alright, so now let's talk about viscosity. Viscosity describes a liquid's resistance to flowing. So let's say I have a beaker full of liquid, like so, and I'm trying to pour it out. Sort of how fast is this liquid going to flow out? Maybe if this were water, it would flow out pretty quickly, but if this was, say, cold molasses syrup, it would come out very slowly. Now, high viscosity, meaning high resistance to flowing, is caused by strong IMFs in the liquid. Temperature is going to affect how strong our IMFs are, and thus how viscous something is. So if I have, say, liquid A, and this one is at 0 degrees Celsius, and this one is at, we'll say, 100 degrees Celsius, this one is going to be much more viscous because our temperature is lower, meaning that the atoms are closer together, and thus our IMFs are stronger, while in this one the opposite is true. And now just a quick note, if something is very viscous, that means that it has a high viscosity. So you would say that syrup is a very viscous liquid. That's just something to know in terms of like vocab or something. Alright, so now let's talk about evaporation. And quick note, this is not to be confused with boiling. These are two very different things. So evaporation does not equal boiling. We'll talk about this a little more later. Alright, so evaporation is where a liquid in an open container is slowly converted to a gas. So let's say I have like a jar of water, and this slowly evaporates and becomes a gas. Now the rate of evaporation depends on the strength of the IMFs of the liquid and the temperature. And so temperature is going to affect our IMF, but it also affects evaporation in a different way, which I'll talk about in a second. So something with very weak IMFs is going to evaporate much faster, while something with strong IMFs are going to evaporate much slower. Now, since temperature in a liquid isn't uniform between all compounds or atoms, some will have a higher kinetic energy and some will have a lower. And this is going to explain why things evaporate. So if we have some liquid here, let's say I have 3 atoms, and the whole thing is at 15 degrees Celsius. This might be at 30, this might be at 15, and this might be at 0. We'll say -1, so it's not confusing. So basically, in a mixture of liquid, not all of the atoms are going to have the same kinetic energy. Some will have higher ones, some will have lower kinetic energies. Now, some of these atoms with higher kinetic energies will reach one known as escape energy, where they now have enough energy to escape as a gas. So let's say here that our escape energy is 20 degrees Celsius, then this atom right here can now evaporate. So that's how evaporation occurs. Now, at a constant temperature, the proportion of molecules that achieve escape energy will remain constant. So maybe 1/10, or maybe it's 1/100th, but this number will remain constant if the temperature stays the same. Now, since only molecules at the surface can evaporate, the surface area of a liquid is a factor in the rate of evaporation. So let's say that I have a beaker like this with 10 liters and one like this that also has 10 liters. This one will evaporate quicker because we have more atoms at the surface. Now, I mentioned earlier that temperature was a factor in evaporation, but that didn't have anything to do with the IMFs. And this is because at a higher temperature, we're going to have more things that will reach escape energy. So if this was, instead of 15 degrees Celsius, let's say 19, we're going to have more atoms reaching the escape energy, and thus more being converted to a gas. So again, factors affecting our evaporation rate are temperature and the strength of the IMFs in a liquid. Alright, so that brings me to vapor pressure. Now, when a container is closed, molecules are still going to evaporate. So I talked about evaporation being in sort of like an open air container. Well, if I have a closed container, like so, these are still going to evaporate. However, these gaseous particles are not going to be able to escape. And so they're going to sort of build the pressure inside my container until an equilibrium pressure is reached. And this is known as vapor pressure. Now, this equilibrium is reached because when these gaseous particles sort of collide, they're going to bounce off and eventually they'll hit the liquid. And when they collide with the liquid, they almost always are going to condense back into liquid form. And my equilibrium happens when the rate of gas being converted back to a liquid is equal to the rate of gas being produced. And that's my vapor pressure equilibrium. And this is known as dynamic equilibrium. Sort of the rates are the same, not that the process has stopped. Now, vapor pressure again depends on IMFs and temperature. And if you think about it, these are both just factors of how fast evaporation is occurring. So that should come as no surprise. Alright, so let's talk about boiling point now. And in the last video, I left you with a challenge problem saying that if something has stronger IMFs, is it going to boil off easier or harder? And so I'll sort of cover that now. The boiling point is referring to when the vapor pressure of a liquid is equal to the atmospheric pressure around it. So if we have water here, and this is at a temperature of 100 degrees Celsius, our vapor pressure here is going to equal the vapor pressure, or the actual pressure outside. And this is our boiling point. And now there's a sort of special boiling point known as the normal boiling point. And this is the boiling point at 1 atm. So when you see that the boiling point of water is 100 degrees Celsius, this refers to the temperature at 1 atm. So that would be the normal boiling point. Now, I sort of said that, or I asked in the last video, if my IMFs are stronger, is something going to evaporate or boil off easier or harder? And so the answer is that if our IMFs are stronger, it is going to have a higher boiling point, because we need more energy to produce more vapor pressure so that it equals the outside pressure. If that doesn't make sense to you, be sure to leave a comment and I'll sort of try to help you out as best I can. Alright, so now let's talk about the heat of vaporization, and this describes the energy necessary to convert 1 gram of a liquid to 1 gram of gas of that liquid at a temperature equal to the boiling point of the liquid. So if we had water's heat of vaporization, which is denoted like so, would be describing how much energy was needed to convert 1 gram of water as a liquid to 1 gram of water vapor at a temperature of 100 degrees Celsius. Now note that this is always positive. Heat must always be added to boil something off. And our differences in the heat of vaporization are related to IMFs. So something with stronger IMFs are going to want to sort of stay together more and won't want to be boiled off and expanded as a gas. So they're going to have a higher heat of vaporization, while something with very weak IMFs will sort of easily spread apart and have a much lower heat of vaporization. Alright, so that brings me to today's challenge problem. Which will have a higher heat of vaporization, water or gasoline? Now, in case you didn't know, gasoline has very weak IMFs, so that should sort of give you a hint. The solution is on our website, learn-ap.com, and I'll also put a direct link in the description. If you guys found this video helpful, please be sure to leave a like and be sure to subscribe for future content. You can like us on Facebook and follow us on Twitter for updates about our new videos and live streams, which we do every Sunday, where we answer your questions about AP Chem, and those are from 5 to 6 p.m. Eastern, again, every Sunday. So links for that stuff will also be in the description. Leave a comment if you're still confused about anything, or also any other comments on the video in general. Other than that, I want to thank you guys for watching, and I'll see you in the next video.